So, okay friends, in lecture 6 we will continue from our discussion from the previous lecture, in which we are discussing about the free endpoint problem. So, what was the free endpoint problem? Just to summarize it, if we have the optimal trajectory x star t and x is vary from x to x plus delta x and t is varying from t to t plus delta t. So, my variation goes here up to the Tf plus delta Tf points, and the basic variation problem we have to solve, in which we are trying to minimize the functional v with the limits from T0 to Tf. And if you recall, in the previous class we have written that the variation can be the increment, we are trying to find out the increment delta j, which was equal to, we have written as delta j1 plus delta j2, where delta j1 we have derived as integral T0 to Tf del v dot by del x minus d by dt del v by del x dot into delta x t. So, this was my first order variation plus the higher order terms into dt. So, and plus del v dot by del x dot evaluated at t equal to Tf into delta x of Tf. So, this we have written as the delta j1, which I am saying equation number 1, and delta j2 we have derived as nothing but, we can say the v dot at t equal to Tf point delta Tf. So, this was our expression for j1 and j2, this we are saying as equation number 2. So, we can see that my delta j is nothing but delta j1 plus delta j2, where j1 is T0 to Tf up to delta x of Tf, this is representing my j1 and this is representing nothing but my j2, where v dot here we can take as the x star t, x dot star t and t. So, next we have to, if we will see, this will have my boundary condition, one is variation in delta x at Tf and another is the variation at the delta Tf. Say at this point delta Tf is missing. So, like in this slide we are missing the delta TF here. So, this is multiplied with delta TF. So, this is my delta J1, this is my delta J2, summation of this will give me the delta J value. In this delta J value, now we have to like delta X of TF, if you will see, my final value is XF. So, I have to see whether delta X of TF can I represent in terms of the delta XF, because my final termination is at T plus delta TF point, where I will have this value as delta XF. So, next we will see can we relate this delta X of TF with delta XF. Say in this figure we can approximate X dot TF plus delta X dot TF as what? So, this is the variation at my terminal point, at these points. Here we are trying to find out X dot plus delta X dot at the TF point. So, we can approximate this result as delta XF minus delta X of TF divided by delta TF. So, this is, if you will see, I am saying this is the delta X of F minus delta X of TF, where delta X of TF is nothing but the value of the X plus delta X at the TF point, and delta at TF plus delta TF point, my value is basically XF plus delta XF, and this is XF plus delta X TF. So, this minus this divided by the time difference, we are saying we are approximating this relation by this value. Cross multiplying, I am having X dot of TF delta TF plus delta X dot of TF delta TF equal to as my delta XF minus delta X of TF. So, I am trying to find out the value of the delta X of TF in terms of the delta XF. Now, if you will concentrate on this, this is the double variation we are finding here, delta X of delta X dot and delta X TF. In our consideration, we are considering only the first order terms. So, we can neglect this term or can approximate it to 0 value. This is due to higher order. So, we can say delta X of TF, if I will try to find out this value, this is nothing but delta XF minus X dot of TF delta TF. So, this delta X of TF we have to place in this expression, which we are saying this is my equation number 1. So, substituting delta XTF in equation 1, and collecting the first order term. And collecting the first order terms. So, we will get nothing but the first variation. Collecting the first order term to represent first variation. So, we are substituting the value of the delta x t f in equation number 1. We are collecting the first order term so that we can represent the first variation. So, the first variation we can write it as, so delta j. So, what we are doing? We are substituting this delta x of T f as delta x f minus delta x dot T f in this equation. So, once we will place this value, so it will have the one term with the x f, other term with the delta T f. So, delta T f we will collect with the second term, and the overall expression can be represented as integral T 0 to T f. So, the integral term will be del v by del x minus d by dt del v by del x dot, this whole multiplied with delta x t dt. So, this is the integral term plus, once we will place it into the equation number 1, my next term will be del v dot by del x dot, and this we have to evaluate at T f point multiplied with delta x f plus the delta T f term will contain the v dot evaluated at t equal to T f point minus del v dot by del x dot evaluated at t equal to T f point multiplied with x dot of T f and the whole expression multiplied with the delta T f. So, this is my first variation, which will contain the first one differential equation, and the last terms will represent the boundary condition with the variation in x T f as well as the variation in the T f. Now, to minimize our functional as per our fundamental theorem, my first variation must be equal to 0. So, this delta j we can equate it to 0. So, equating this to 0 means what? My integral term as well as the boundary condition, they all must be separately equal to 0 due to my fundamental lemma, as we have discussed in the previous lectures. So, if delta j equal to 0, so I can say del v dot by del x minus d by dt del v by del x dot delta xt is equal to 0, and this we are writing from the first term. From this term we can write this. So, delta xt is arbitrary, therefore, the coefficient of the delta xt that must be equal to 0. This means del v dot by del x minus d by dt del v by del x dot, that must be equal to 0, and this is nothing but my Euler equation. Subjected to this, I will have the boundary conditions. This means del v dot by del x dot at t equal to Tf point, I am evaluating this with delta xf plus v dot at t equal to Tf point minus del v dot by del x dot, again evaluating at t equal to Tf point, x dot of Tf delta Tf, that will be equal to 0. So, this is the boundary condition, and this is my Euler equation to find out the optimum value of a given functional. So, if I will consider my basic variational problem as a free endpoint problem, I will lead to the Euler equation given by del v by del x minus d by dt del v by del x dot equal to 0, and the boundary condition is del v by del x dot delta xf plus del v dot evaluated at t equal to Tf point, del v by del x dot evaluated at t equal to Tf point, x dot Tf delta Tf equal to 0, and where v dot we are representing as nothing but the value of the v at optimal point x star, x dot star and t. So, this will we finally have these two equations. Now, the free endpoint problem can appear in a different manners. So, in the next we will see what may be the different cases as my final point is what we are saying. In this case my we are saying my xtf is free, so it can terminate to some other point, simultaneously the tf is free. If you can recall, in the first case we have taken that the fixed endpoint problem. In the fixed endpoint problem, my initial and the terminal point was fixed. So, we will try to apply, we will apply our different cases to my final result and see what may be the different cases may be for a free endpoint problem. So, we take the first case, which was the fixed endpoint problem. So, what is my fixed endpoint problem? I am given with the T0, this is x0, and let this is my x star. So, my TF is also fixed as well as the final XF is also fixed. So, in this case, if I will have the variation as x star plus delta x. So, if my terminal points are fixed, so I can say my first equation will be my Euler equation, and the boundary condition as my terminal point is fixed. So, delta xf will be 0, and with the same logic my delta Tf will also be 0, because there is no variation in Tf at this point and there is no variation in the x at this point. So, this particular case my these two will be 0, and to find out the minimal we have to solve only the my given Euler equation. The one example we have seen in the previous class, once we are trying to find out the minimal length of the between the 2 points. So, these 2 points we already have been fixed. So, this problem already we have been taken previously. So, this general problem can be converted into the fixed endpoint problem if we will consider the delta x of f and delta t of f to 0. So, my second equation will not appear in that particular case. Next we will take the another case. So, in second case I have Tf is specified and xtf is free. So, what is this case? If this is t, this is xt. So, what we are saying, my Tf is specified. So, this means let us say this is T0, this is Tf. So, this Tf is specified. In addition to this, we are also given with the T0, xt0. So, my trajectory, let us say this is my optimal trajectory x star. So, by the variation of this can terminate to any point, because my xtf is free. So, if there is a variation on the x star, so my final trajectory can terminate to any point on the Tf line. So, in this case as the Tf is fixed, so naturally my delta Tf, this delta Tf will be 0. So, this means delta Tf will be 0 in this case, and my problem is, so endpoint is left with only the del v by del x dot evaluated at t equal to Tf point delta xf equal to 0, and here delta xf is arbitrary So, this means del v by del x dot Tf, T we are taking as Tf, this will be 0, or this we can also write as, this means delta V x of Tf, x dot of Tf, Tf by delta x dot of Tf, this must be equal to 0. So, to solve such a problem, first we will solve the EL equation given as del v by del x minus d by dt, del v by del x dot equal to 0. This will lead to a differential equation which we have to solve subjected to the initial condition given as the T0 xt0 and the final condition if Tf is fixed, xtf is free. So, this will represent my final point condition. So, how to implement this, that we will see using an example. So, just to consider the case 2, we take an example. Our objective is to determine the connecting the point x0 equal to 1 to the line t equal to 5. So, my problem here is I have to determine the curve of the smallest distance which is given as x0 equal to 1 from this point to a line given as Tf equal to 5 and this is my xt. So, this point can terminate to this, let this is my optimal x star t. So, if this is terminating to this, my objective is to find the shortest distance so that the x0 equal to 1 will have the line Tf equal to 5. So, in the first problem we have taken that between the 2 points we are trying to find out the shortest distance. So, if this is my xt, I can write my distance which is nothing but my objective function in the similar manner as we have done it before from 0 to 5 with ds. And what was the ds? My ds was 1 plus x dot square t square root into dt. So, in the similar manner we are taking a small ds, if this is my dt, this is my dx and this is my ds. So, this ds integrating from 0 to 5, I am finding out what is the length of my curve. My objective here is I have to determine the minimal length of this curve, means what is my optimal x star t, that is my objective to find out. So, in this case my TF is fixed, but XTF is free. For the minimal it can go to anywhere. So, in such case my first step is, first I will solve Euler equation, which is del V by del x minus d by dt del V by del x dot, that must be equal to 0. In this case I am given with the V is nothing but 1 plus x dot square t So, if I will find, use V here in EL equation. So, what this will give me, del V by del x, it is independent of this 0 minus d by dt of x dot t 1 plus x dot square t this must be equal to 0, and this nothing but can be written as x double dot t equal to 0. So, the solution of this Euler equation giving me x double dot t equal to 0. Now, the solution of this solution of x double dot equal to 0 is, this we can directly write as x t equal to C1 t plus C2, and nothing but this is my optimal x star. So, this optimal x star is in the form of the C1 and C2. So, my objective here is next to find the value of the C1 and C2 using the end point conditions. My initial condition is given with to me t equal to 0, value of the x equal to 1, at t equal to 0, x 0 equal to 1. So, this means 1 equal to t 0, this is 0. So, C2, this means my C2 is nothing but equal to 1. So, the one constant C2 I can directly find out using my initial condition. My next aim is to find out the another constant C1. C1 we can find out if my terminal condition is given. So, in this case what is my terminal condition? My delta TF is 0. So, del V by del x dot TF, that must be equal to 0. So, another terminal condition is del V dot by del x dot, which we are evaluating at t equal to TF point, that is equal to 0. I was given with the V as 1 plus x dot square t 1 by 2. this is V. So, del V by del x dot if I will take at t equal to Tf point, this is nothing but, because Tf is 5, 1 plus half equal to 0. This means this is giving me x dot 5 equal to 0. X dot 5 equal to 0, but this is my x t. If I will differentiate this, so this give me x dot t as nothing but C1. So, this means x dot 5 is nothing but my C1, and which is the value 0. So, I have my two constant as C1 equal to 0 and C2 equal to 1. So, my optimal trajectory will be x star t is nothing but, as C1 is 0, C2 is 1. So, x star t equal to 1 is my solution of this, and this we can see it here. The minimal distance between this point is nothing but a line parallel to t axis, and this is my x star t equal to 1 is the solution. So, by this we find the optimal solution for my given problem is x star t equal to 1, and this x if we will use in this, so I can find out the minimal length of this, my value of the j with x star t equal to 1, j can be determined, which is give you the what is the minimal length between these 2 points. So, we stop this lecture here, and we will continue the free end point problem in the next class. Thank you very much.